Okay. Now we go to this, and we had already seen these two types of subsets. Okay, matchings, particular subsets of the edge set, coverings, particular sets of vertices. Okay, and there was a connection between them which gave us that the number of matching of edges in a matching is always less than or equal to the number of vertices in a covering. And for bipartite graphs, that the number of edges in a maximum matching is equal to the number of vertices in a minimum covering. Now we'll have two more interesting sets, which are these independent sets and edge coverings. Okay. And we'll see the interaction between all these, and also I hope that we'll also be able to say something about cliques. Okay. A subset S of V is called an independent set of G if no two vertices of S are adjacent in G. An independent set is maximum if G has no independent set S prime with the number of elements in S prime greater than the number of elements in S. Okay, and in 7.1 we can see independent sets. Okay, they are interesting for telecommunication people in particular, because if you have senders that may interfere with each other, then you want to pick up a set of independent vertices, in the sense that an independent set, if you put a vertex for each transmitter and an edge between two transmitters, if they may interfere, then an independent set is a set which has no interference. Okay, and it's useful for, in particular, in the military domain, but I'm not going through it now. Okay. A subset K of V such that every edge of G has at least one end in K is called a covering, that we already saw in the previous chapter. Actually, a set S of vertices is independent if and only if its complement V minus S is a covering of G. Let's see why. By definition, S is an independent set of G if and only if no edge of G has both ends in S. Okay? Because if an edge has both ends in S, it means that those two vertices are actually adjacent, so they cannot be part of an independent set. So every edge either has no end in S or has at most one end in S. Okay? But this means that it has at least one and possibly two, both ends in the complement V minus S. Okay, but this happens if and only if V minus S itself is a covering. Okay, so a set is an independent if it and only if its complement is a covering. So we can also already put it. They are both sets of vertices, and they are complementary to each other. The number of vertices, oh no, let's have a look here. And so, Here we have an independent set. Okay, again, look at the way the mathematicians do. Look at these extreme situations. Do you want, I wake you up at 3 in the night, okay, let's say on Wednesday, because on Saturday, I don't know, maybe you are still awake at 3 in the night, okay? On Wednesday night, I wake you up at 3 o'clock and I tell you, here is a graph, give me an independent set. Then you can say, this vertex, and then go to sleep again, okay? And it's all right, okay? Because a vertex by itself satisfies the requirement for a set to be independent. Okay, so this is all right. Okay, and also let me say something which is not on the book, but even if it is so small, it is a maximal independent set, in the sense that if you dare adding even one other vertex, you do not get an independent set anymore. Add any one of these and you don't get an independent set anymore. Okay, so even if it's so small and very far from being a maximum independent set, still it is maximal in the sense that there is no independent set in the graph containing it properly. Okay, and here you have a maximum independent set. On the contrary, it is independent, all right, and it is actually, you can try with what? With brute force. You would write down all possible sets of vertices with the 3 vertices, and you'll see that it's impossible to have a set of an independent set of 3 vertices. Okay, all right. I'm sorry, but okay. This is the maximum one. Of course, being maximum, it is also maximal. Okay, this is maximum without being maximum. And again, what you see is that if you take the complement is a covering in the sense we have seen in a previous chapter. Okay? Now, what you have is this called alpha, the independence number, which is the number of vertices in a maximum independent set of G. And beta, the covering number, which is the number of vertices in a minimum covering. Again, sorry, you were already sleeping away. No, I wake you up and I say, no, now give me a covering of the graph, okay? What can you give me? All the vertices, and you go to sleep again. And that's correct, okay? They are extreme and exactly what we are not interested in. Why? Because we want a lot of independent vertices and few vertices in a covering. As engineers, you want, if you are considering a concept, you want to optimize that thing, okay? And so you want to save vertices in a covering and exceed, if possible, vertices in an independent set, okay? You want, taking the example I was given before, you want active as many transmitters as you can in your network, okay? You see what I mean? All right. And what we have is, as a corollary what we had before, that if you take these sums of the sum of these numbers of maximum number of vertices in an independent set alpha and minimum number of vertices in a covering beta, alpha plus beta is ni. Let's see. Pick up a maximum independent set of G and K be a minimum covering. Then V minus K, so the complement of this minimum covering, is an independent set, okay? And if you take the complementary of S, it is A covering, okay? But then what we have is that the number of vertices in the complement of the sorry, in the complement of the minimum covering. Okay, so K is a minimum covering, so its number of vertices is exactly beta. Okay, and the complement V minus K has necessarily cardinality, number of elements, Ni minus beta. And what we get in V minus K is an independent set. So we do, for this moment, so far we do not know whether it is maximum or not. But still, it's the number of elements in an independent set. So this number, Ni minus beta, must be less than or equal to alpha. In exactly the same way, S is an independent set, a maximum independent set. V minus S is a covering. We do not know whether it is minimum or not for the moment, okay? But it is a covering, and how many vertices does it have? Ni minus alpha. And so we have that this number of vertices in a covering must be greater than or equal to the minimum number of vertices in a covering, which is beta. And so we get these two inequalities, okay? But then take beta to the right here, and you get Ni less than or equal to alpha plus beta. Take alpha to the right here, and you get Ni greater than or equal to alpha plus beta. Okay, take this to the right, this to the right, and you get that alpha plus beta is greater than or equal to Ni and less than or equal to Ni, so it is equal to Ni. Okay, now let's go to the edge analog of an independent set. It is what? It is a matching. Okay, what is an independent set? A set of vertices, no two of which are adjacent. What is a matching? A set of edges, no two of which are adjacent again. So what corresponds to an independent set in terms of edges is already has been already studied. It's a matching. Okay, but let's talk about the edge analog of a covering. It is called an edge covering. What is it? A subset of the edge set, such that each vertex of G is an end of some edge in L. Okay? You're not sure that this exists. Why? Because you might have isolated vertices with a small delta equal to 0. And so, if you have an isolated vertex, a vertex by itself, not joined to any other vertex in the graph, then it's not possible to have an edge covering in that case. Okay, so not always there exists an edge covering. Instead, there is always a vertex covering, meaning the 3 o'clock in the night one I said, take all the vertices, you have a vertex covering. Take all the edges, it's not sure that this is an edge covering. Why? Because you might have an isolated vertex. Okay? But we denote the number of edges in a maximum matching of G by alpha prime of G, and the number of edges in a minimum edge covering of G by beta prime of G, which are edge independence number, edge covering number of G respectively. It's not as we had the same thing that we had before. The complement of a matching need not be an edge covering, nor is the complement of an edge covering necessarily a matching, okay? Always because of these vertices of degree 0. So, it's rather spectacular, I would say, incredible, that even if you do not have such simple proofs as we had for the relation of before, alpha plus beta equal to Ni, which was straightforward, then here things are different, but still, incredibly, we have the same relation. Alpha prime plus beta prime equals ni, okay? Of which I do not give a proof. And we have a theorem, Koenig's, no, it's not Koenig's theorem, but it resembles Koenig's theorem. In a bipartite graph with no isolated vertices, delta, small delta greater than 0, the number of vertices in a minimum independent set is equal to the number of edges in a minimum edge covering. So we have for bipartite graphs, we have this relation. I told you since the beginning, bipartite graphs are interesting for two things. For engineers, because they represent very many particular situations in which you have two types of objects related together, but of different nature. Teachers and classes, men and women, and so on, okay? And so they are an interest because many applications are directly modeled on bipartite graphs. And also from the theoretical viewpoint, because there are particular theorems which hold exactly for bipartite graphs, as this one, okay? So for the moment, we can complete our not complete, but go on with our things here, and which is that if we take an independent set and an edge covering, you have that you for bipartite graphs. Okay, my resuming thing is that in a bipartite, you have that the number of minimum edge covering equals the number of maximum independent set. And also here that alpha prime plus beta prime equals ni, and also here alpha plus beta equals ni. Okay? And we now have to talk about 34. Ramsey's theorem. Ramsey's theorem is very, very interesting because at the first time I saw it, I didn't believe in it. And unfortunately, many students don't understand really what this theorem says, which is very, very interesting. Okay, let's see from a rough viewpoint. If you have a graph with quite a lot of edges, close to a complete graph, but you see that it's full of edges, quite a lot. Do you think that it's easier that it has inside subgraphs which are complete, which are called clique? What is a clique of a simple graph? A subset of vertices such that the induced graph is complete. So a set of vertices all join to each other, okay? This is a clique. So if you have quite a lot of edges, do you think it's easier to find big cliques or big independent sets? Big cliques, possibly, okay? If it is very sparse, so a few edges, maybe it is connected, okay? But you see that quite a lot of vertices and only a few edges, then my bet would be I can find a big independent set and maybe small cliques, okay? A clique is already a vertex by itself, is a click of one vertex, okay? An edge is a click of two vertices because I pick up these two vertices and these two vertices and the edge between them is already a complete graph with two vertices, okay? You need a triangle to have a click of three, okay. All right, so intuitively, that's all right. The more likely you have big clicks, the less likely you have big independent sets, and conversely. Okay, but I'm not going to talk about probability. This is the interesting thing. It's not what I'm going to say is not a probabilistic thing. Look, Ramsey, how old are you in general? Hmm? Okay. Oh, yeah, okay, you're very young. But Ramsey was not too old when he discovered these things. He died because of an operation, a stupid operation, at the age 27. Okay, and he did quite a lot of things, and this is just a part of his general principle. The incredible thing is this. He showed that take any positive integer k and l, okay? There is for each pair k and l a certain number called the Ramsey number for that pair of integers, such that every graph with at least that number of vertices contains either a clique of k or an independent set of L vertices. No matter how you draw it. If, let's go here. This is the table which was known at the time of this book, so quite a long time ago. Now, if you look in Wikipedia, you find the table which is bigger, but not terribly bigger. There are very many intervals. But here, it says what? If you pick up any graph, which you can imagine with at least 14 vertices, this says that either it contains a clique of 3 or an independent set of 5. However you draw it, you are free to draw it, but if it has at least 14 vertices, you cannot avoid it to have either a clique of 3 or an independent set of 5. If you draw one of degree with at least 18 vertices, necessarily it will have either a clique of 4 or an independent set of 4. You are not free. It says Ramsey. You are not free to rule both things. Okay? If you have at least this number of vertices, either you have this or you have that. And that's really heavy as a thing. It all comes from this particular theorem and from the start. This is a recursive theorem. But let's reason on the small numbers, okay? They say that R1L equals RK1 and it's equal to 1. Meaning that whenever you have one vertex, either you have a clique of 1 or an independent set of 1. Necessarily because what? A clique of 1, of L, sorry. Meaning that when you have any graph with at least one vertex, surely you have a clique of 1. A clique of 1 is one vertex by itself. Okay? And surely you have an independent set of 1, because a set of 1 vertex is always independent. So this is a rather stupid thing, but of course, as always, in mathematics, the first steps are always rather silly. Next are a little bit more interesting. And it says R of 2L equals L. What does that mean? It means that, let's take a number, L equal 10, okay? So we can understand better what we are saying. It says the Ramsey number of the pair 2, 10 is 10, meaning if you take any possible graph with at least 10 vertices, either it has a clique of 2 or it has an independent set of 10. Can you see that? What is a clique of 2? I already told you. Hmm? What is a clique of 2? Just an edge. So if you have at least one edge, you are already done because you have a clique of 2. Otherwise, there is no clique of 2. It means that you have no edges. But then it means that this graph is empty of edges. And so all vertices, the set of all vertices, is itself an independent set. Okay? And our K2, more or less in the same situation. Let's take now K equal 20. Okay? 2 equals 20. What does it mean? If you pick up if you draw any graph with at least 20 vertices, either it has a clique of 20 or it has an independent set of 2. What is an independent set of 2 vertices? Two vertices which are not adjacent, for which there does not exist an edge between them. Okay? So, are there two vertices not joined together? Then you have your independent set of 2. No, I'm sorry. However, you pick up two vertices, there is an edge between them. But then what is your graph? Your graph is the complete graph on k vertices, in our case 20 vertices. So there is a clique of 20. Okay, so a little bit more tricky, but it's obvious that we have these numbers. But now it is possible, this is um, this is one way to get to the general Ramsey theorem. If you have any two integers, k and l, both greater than or equal to 2, RKL exists and is less than or equal to the sum of these two, RKL minus 1, RK minus 1L. Okay, and furthermore, if these two numbers are both even, then the inequality is strict. Okay, and then how can you determine some of these Ramsey numbers that we have seen? Let's see, for instance, this. Okay, how we can say that. So our R33 is greater than or equal to 6. Why? Because we have such what is called a Ramsey graph, in which we have 5 vertices, and here you do not have a clique of 3, you do not have a triangle, and you do not have an independent set of 3, because however you pick up 3 vertices, at least two of them are adjacent. So this shows that R33 is greater than or equal to 6. But then what you have is that you have what? That out of the theorem we have seen, R33 is less than or equal to R32 plus R23. But we know R32 and R23. They are both 3. We had that in the things before. Okay, we saw before. Here, okay, we already know that R23 is 3, R32 is 3. And so, out of the inequality, we get that R34, that R33 is less than this, but it has to be greater than or equal to 6 because of the existence of this Ramsey graph. And so we know that actually R33 equals 6. And so this is a way how we can get R33. But then you can use other Ramsey graphs for which you can see, out of which you can see that certain Ramsey numbers necessarily are greater than or equal to certain numbers, and you get, in this way, more or less, you get these numbers. Okay? All right. I think that this is extremely interesting because it tells you once more that you are not as free as you could imagine when you draw a graph. The first opportunity for that was when we saw that it's not possible to have an odd number of vertices of odd degree. Okay, very simple. And now you know something even more striking, in my opinion, that these are what you get, and there are more known. Look at Wikipedia, and you'll see that at least for some Ramsey numbers, you know in which interval they are, but still you don't know what they are. But there is a number which is such that if you take any graph with at least that number of vertices, either click or K or an independent set of L must be there. Such a number exists. But we still don't know how much it is out of this table or something which is not much bigger than this. Okay, see you tomorrow.